We're continuing our discussion of the timer circuit. In part B and part C, we found the time constant during the charging phase and discharging phase. Now, in part D, what length of time passes between subsequent 10-volt output voltages? Remember that we alternate the voltage between 5 volts and 10 volts. So 5 volts to 10 volts is charging, 10 volts to 5 volts is discharging. So we want to know how long passes between subsequent 10 volts output voltages. So to answer this question, I want to start out by noting the charge as a function of time during the charging process. During the charging process, the type of solution I have for Q of t is Q maximum 1 minus e to the minus t over the time constant for the charging phase. This is when I'm going from, this is going to be valid as I go from 5 volts to 10 volts. Now you can see if you wait long enough as t goes to infinity, this is going to be e to the minus infinity, which is 0, and I will have the maximum charge stored. At t is equal to 0 here, I have no charge stored. So that's the form of the solution for Q of t. But I will only operate between 5 volts and 10 volts output voltage. And what is the form of the solution for Q of t during discharging? This I mentioned in part C to calculate the time constant. The form of the solution is Q0 plus Qmax e to the minus t over the time constant for the discharging phase, and this equation will apply as I go from 10 volts to 5 volts. Okay, now if I'm at 5 volts, I will have the charge stored to be 5C, Q is equal to Vc. If I have 10 volts output voltage, the charge stored will be equal to 10 times the capacitance. So what is the charge stored at t is equal to T1? T1 is the time when I have 5 volts, so that is 5C. So I can take one of these equations. Let's take the charging equation. The charging equation says I have Qmax 1 minus e to the minus t1 divided by tau c, and at time t2 I have reached 10 volts. The charge is 10C, which is going to be Qmax 1 minus e to the minus t2 over tau c, the charging process, for the charging process. Okay, so I have for the charging portion of the cycle, basically these two equations. So that tells me that 1 minus, let's write here, because I already know that Qmax is equal to 15C, this tells me that 1 minus exponential minus T1 over tau C should be equal to 5 divided by 15, which is 1 over 3. Therefore, the time T1 when I have 5 volts appearing here will be equal to 1 minus 1 over 3. So you can see here I will have 1 minus 1 over 3. So this is going to give me 2 over 3 is equal to exponential minus t1 over tau c, which was found in part B to be 4RC. So t1 over 4RC. So that tells me that t1 time t1 is 4RC natural logarithm 3 divided by 2. So it's natural logarithm 2 divided by 3, but there's a minus sign, so it becomes natural logarithm 3 divided by 2. And the time when I have 1 minus e to the minus t2 over tau c equals 10 over 15, which is 2 over 3. That means I have 1 over 3 is equal to exponential minus t2 over 4RC. So that gives me t2 is equal to 4RC natural logarithm 3. So the total time passes during the charging phase is t2 minus t1, which is 4RC natural logarithm 3 minus 4RC natural logarithm 3 over 2. And that gives me, for the charging process, the time passes to be 4RC natural logarithm 2. So that's the time that passes during the charging process, 4RC natural logarithm 2. Now let me concentrate on the discharging process. During the discharge, I have the charge at T2, at time T2, which is 3C plus Qmax e to the minus T2 divided by the discharge time constant to be equal to 10C. So first I start at 10 volts, and then at time T3 I reach 5 volts. So this will be 3C plus Qmax e to the minus T3 divided by the discharge time constant must be equal to 5C. So that's going from 10 volts back to 5 volts. So this tells me that because Qmax is known to be 15C, 15C e to the minus T2 over tau discharge must be equal to 7C, and 15C e to the minus T3 over tau discharge must be equal to 2C. So that's 5C minus 3C. So if I divide these two, what am I going to obtain? The 15 C's will cancel out, and these C's will cancel out as well. I will see that e to the minus T2 minus T3 divided by tau discharge is equal to 7 divided by 2. So this implies e to the T3 minus T2 over tau discharge is equal to 7 over 2. Because I've operated this minus sign, it's minus T2 plus T3. And this tells me that T3 minus T2 divided by tau discharge, which I found in part C to be 4RC divided by 5, is equal to natural logarithm 7 over 2. So this tells me, because T3 minus T2 is the delta T in the discharge process, delta T discharge is 4RC divided by 5 natural logarithm 7 over 2. So that's the time that passes during the discharge cycle. So I start at 5 volts, I reach 10 volts, then I start at 10 volts, I reach 5 volts. So between two consecutive 5 volts, I have one period, or between two consecutive 10 volts, I have one period. It is the charging time plus the discharging time in each cycle. The charging time I have found to be 4RC natural logarithm 2. The discharging time is 4RC divided by 5 natural logarithm 7 over 2. So this can be rewritten as 4RC natural logarithm 2 plus 4RC over 5 natural logarithm of 7 minus 4RC over 5 natural logarithm of 2, which is equal to 5 times 4, 20 minus 4, 16. 16 RC divided by 5 natural logarithm 2 plus 4 RC divided by 5 natural logarithm of 7. In other words, the period can be written in 4 RC over 5 parentheses as natural logarithm of 7 plus 4 natural logarithm of 2. So that's the answer to part D. The time that passes between two consecutive 5 volts, which is equal to the time passes that between two consecutive 10 volts. Now part E. If R is 10 kilo ohms, C is 10 microfarads, what is the frequency of operation? Note that this circuit is a simplified example of a timer circuit, a crucial element in many electronics applications. R and C values are given, so I can put R is equal to 10 kilo ohms, C is equal to 10 microfarads. The RC time constant is then 10 times 10 to 3 ohms times 10 times 10 to minus 6 farads, which is 0.1 seconds. That's the RC time constant. Then the period will be 4 times RC, which is 0.4 divided by 5. Natural logarithm of 7 plus 4 natural logarithm of 2. And this turns out to be 0.377 seconds. And the frequency is 1 over the period. So the frequency of operation is 2.65 Hertz. And that's the answer to part E. Okay, so in part D of this question, I have considered the charge as a function of time during the charging process. So if a capacitor is charging, as t goes to infinity, it will reach a maximum charge. And at t is equal to 0, it's going to have no charge. So that's describing the charging process. At t is equal to 0, 1 minus 1 is 0, I have no charge. As t goes to infinity, I have Qmax. During the discharging process, I start with, if I have a charge Q0, as t goes to infinity, it's not completely discharging, then I have a charge Q0 as t goes to infinity. And if I have at t is equal to 0 here, I'm going to have Qmax plus, so that's going to give me, if you put t is equal to 0 here, it's going to give you Qmax plus Q0 for the charge, but that's basically not going to apply here, because as t goes to infinity, we're going to cut the process of discharging and start charging again. So as t goes to infinity, we need to have a charge Q0, and because it's a discharge process, the charge must be decreasing. So as time increases, we're going to see that this portion will decrease. Okay, so this is assuming that at t is equal to 0, we start at Qmax. So for the discharge process, we would have Qmax times e to the minus t over tau d. But here I'm noting that there is an initial charge Q0 at t is equal to 0. At t is equal to infinity, there's a remaining charge Q0. So that's basically what I have to consider here during the discharging process. Okay, so I start at 5 volts, I reach 10 volts during the charging process. So 5 volts, the charge is 5C. At 10 volts, the charge will be 10C. If I write down 5C for t is equal to t1 and 10C for the charge at t is equal to t2, I find that the time that passes is 4RC natural logarithm 2, that's t2 minus t1. During the discharge process, at time t is equal to t2, I must have 10C, and at time t is equal to t3, I must have 5C. I'm going back from 10 volts to 5 volts. The charge goes from 10C to 5C. I see that the time that elapses is 4RC over 5, natural logarithm 7 over 2. If I add these two, I find the period. I started at 5, I went to 10, and then I went back from 10 to 5. Now, if I have R is equal to 10 kilo ohms, C is equal to 10 microfarads, RC time constant is 0.1 seconds, so I can substitute that to find the period. 1 over the period is the frequency of operation, which is 2.65 hertz. And remember that the way I have reached this equation for the discharge process was by writing the equation of motion in part C for the discharge process, and I have found that this solution will satisfy this equation provided that Q0 is equal to 3C and the discharge time is equal to 4RC over 5. So that's basically what I did to make sure that this will solve the differential equation for the charge as a function of time.